Okay, so just before we get started on this, I just want to make it clear that the code for this presentation is going to be located in the programming patterns directory of the dev conference extension in the version 12.0 branch. Okay, so this presentation is going to basically end up being about software development patterns and their use in CM. We're going to go through 3 development patterns, demonstrate a use case for them, talk about their pros and cons. But before we actually do any of that, let's talk about how you actually want to go about choosing these patterns in the first place. So some of the, there we go. Some of the main do's here are, the biggest one is make sure you're choosing a pattern based on the problem. So what I mean by this is when you're trying to solve a problem in your code and you're trying to apply a specific software development pattern, you need to make sure that you're actually choosing your pattern based on the problem and not the other way around. So don't try and shove a square peg into a circular hole here. Also, try and keep your patterns as pure as possible. And again, what I mean by that is when you actually start your development and you say, this is the pattern I'm going to use and this is the way I am going to use it, try to stick to that throughout your development process. And another big thing is there's a lot of software development patterns out there. Always double check your choice. I've even in this presentation, multiple times when I thought I had the right pattern to the problem, I ended up actually going back and changing the pattern that I was going to use because I realized there was a better fit. So some of the major don'ts are, as kind of a counter to the first do there, don't adjust your pattern to match the problem. One of the major problems I see when I've personally gone to implement something like this is I will frequently find myself trying to squish a problem into the pattern that I want to use, even though it doesn't fit. Also, creating excessive exceptions to the problem and your exceptions to your pattern when you're developing generally ends up causing a lot of spaghetti code and kludge. So fitting with that theme of fitting a pattern to the problem that you actually have, let's start with a problem. So we have a problem where we want to communicate between different objects. We want to do it efficiently, meaning we're not going to be sending or receiving more information than is actually necessary. We want to do it anonymously, in that we don't want to care who is sending or who is receiving the information. We want to do it abstractly, in that we don't care what the types are of who is sending and receiving the information. And we want to try to do it at we want to be able to ask for information at runtime. So this doesn't have to be hard coded. So the pattern that we're going to use to end up solving this problem, we also want to do it independently. So the object that is sending out this information in the communication doesn't actually have to know about anyone else involved, any other objects involved. So the pattern that we're going to end up using for this problem is going to be the observer pattern here. So this pattern is a fairly simple pattern that is basically based on the relationship between 2 separate objects, the subject and the observer. So this is a event-based communication system pattern. So where we go with that is the subject broadcasts events that the observer has subscribed to. So we're going to see some further examples of that later on. But the really important part about these 2 things is that the subscription part of this makes sure that any events received by the observer are only events that the observer asked for. So if you've ever seen a system where you're receiving every single thing that happens, that subscription bit is what kind of narrows down the scope of the actual information that you receive. Another very, very, very similar pattern to this that we won't be talking too much more about, but I wanted to bring up because I think it's important, is the publish subscribe pattern. So this is nearly identical to the observer pattern, except that there is an event handler located in between your publisher and your subscriber. So what that means here is that your publisher, when it emits an event, it emits it to the event handler. And your subscribers, when they subscribe to an event, subscribed to the event handler itself. So this just kind of creates a little more separation, or even more separation between the subscriber and the publisher, or in the observer pattern case, the observer and the subject, than we already had in the observer pattern. So what would be the actual use case of this in CM? Well, there's plenty of times in my own personal CM development that I've had to transfer information between a snapper and a snapper, or a snapper and a component, or coming up in the future here soon, probably sending information between a snapper and a child snapper. And so a lot of the time there are lots and lots and lots of different pieces of information that need to be transferred between these two. So just some of the examples I have here, I mean, dimension changing, position changing, materials changing, and so on and so on. So how can we use the observer pattern then to solve this problem? So let's start with actually defining that subject half of things. So in this case, I'm going to be creating a system that is based on the communication between a snapper and a component in an event-based observer pattern. So right here, you'll see that we have two very, very important methods. We have the subscribe method and the broadcast method. The subscribe method is what the component is going to call on the snapper here to basically say that I want to receive some specific piece of information. In this case, I am using a symbol to represent the type of information and the key to represent the specific component that is asking to be subscribed. Then we also have the broadcast method on our subject snapper. So what this is going to do is at any point in the snapper's functionality, that something happens that it needs to send out an event to all of its subscribers, it's going to end up calling this broadcast method. So this is basically a central dispatch point for an event and a value related to that event. In this case, if it were a width changed event, the value would contain the new width, or a material changed event, the value would contain the new material. You'll also notice that we expose these through XAPI, or the subscribe method specifically through XAPI. And for those here who haven't used XAPI before, at its most simple, it is just a method or a way to call methods on an object without actually having to know the type of the method object or whether or not it has that method in the first place. We also are exposing a get events method through XAPI. This isn't actually necessarily part of the of the observer pattern, but it's very helpful. I noticed in my own development of this, if the component can actually ask, hey, these are the different what are the different types of things that I can subscribe to? So now talking more about that component, so we can move on to the observing component here. So there are a couple really important methods here. The most important one is this receive event. So just like broadcast on the subject snapper was the central dispatch point for all events, this is the central reception point for all events. Again, we are exposing it through XAPI, so the snapper does not actually have to know our type. Nor know if we even have a receive event method. It can just loop through all of the components that have subscribed to it and call the XAPI call to broadcast out that event. In this scenario, we also have an init subscriptions method due to component not having an owner. So generally the pattern on component is any method that needs information about its owner will take its owner in as a parameter. So that is what is happening here. So when the component is added on to the subject snapper, init subscriptions will be called and the owner will be passed in so that the component can then subscribe to all of the events that it wants to ask for. So now let's talk about an actual real life example of now using that system that we have built. So what we have here is we have a lounge seat. So for those who haven't done too much development in that side of things, we're basically just going to be talking about the rough equivalent of a couch. So this is going to be a couch that ends up having a back cushion and a bottom cushion, both as separate components. So this lounge seat here, as you'll notice, has a set material and a set width method. When the material is changed, it broadcasts that the material is changed. And when the width is changed, it broadcasts that the width is changed. This would then be piped based on who has subscribed to the width changed or material changed event to the respective components. So then going more into the specific component, we can then see that we can receive the events and act based on the events that we received. So in this case, when our material changes, we can set our material to the respective material, and when our width changes, we can change our width based on, not necessarily to, but based on the width of whoever sent out that width changed event. So what this ends up looking like in the end is something like this, where we have, sorry about that, where we have a lounge seat, a back cushion, and a top cushion, which is in red right here, which automatically adjust their width based on the width of the lounge. The back seat specifically is the only one subscribing to the height event, so it is the only one who changes its height based on the change. And then as you noticed there, the material change event, which changes it to a different material based on the material that the lounge is originally set to. So what are some pros and cons of actually choosing this pattern for your software, for your problem and your software development? So some of the biggest pros that you can find by using the observer pattern and sticking to the observer pattern is that you get reduced casting. So when you go and look at the code samples that we generated for this lounge, you'll notice that there is not a single point where we actually cast the component or cast the subject snapper to check whether or not they can receive or send out this information. So the lounge is blind to the cushions, and the cushions are blind to the lounge, except for that event-based notification system. You also received reduced dependency on the actual creator. So what I mean by this is, as I mentioned, the cushions were blind, which means that they didn't have to depend on whoever owns them to know that they own them and know to set their width. They can just say, I am subscribing to any width change events you have, and as long as the subject snapper is sending out those width change events, then it knows that it can do what it needs to do. We also receive blind communication here, which is kind of further extending off of that reduced casting, in that no one needs to know, or no specific object needs to know about any other object in this system. So some of the major cons that you can end up getting from using the observer pattern in your development are no guaranteed linearity of events. So if there was an example, say, where the back cushion of that couch we made needs to be updated before the base cushion of that couch, we wouldn't necessarily be able to do that without modifying the pattern to add some sort of priority or linearity in the events. It can possibly be a bit difficult to debug because of these central dispatch points and central reception points. So contrary to having a adjust width to couch method, for example, you would always know that if there is a bug with adjusting width to couch, it would be located in that adjust width to couch method, where you don't really get that in this event-based system. You also end up having a large lack of parental control over these objects. This actually kind of counters that some of the pros of the reduced dependency on the creator, in that if let's say your lounge only needs to change the width of its base cushions or the material of its base cushions sometimes, but not all the time, it wouldn't have the control to make those decisions in this pattern. So what are some alternative patterns that we might have been able to pick to solve this problem? Well, there's the publish subscribe pattern, which we mentioned earlier. There's the command pattern, the chain of responsibility pattern, which is based on another event-based notification system where it just keeps sending events down through objects until one object claims responsibility for it, and then that event ends there. There's the mediator pattern, and just it kind of goes so on and so on from there. And this is where I was getting into at the start of this presentation, where always double check your pattern choice. There are so many of these, and they're all designed to solve specific problems. There's a good chance that there's one that ends up working better than the rest. So let's move on to another problem. So let's say we want a system where we have to create many, many different types of similar objects with per object functionality. We want a lot of code reuse. We want to reuse as much code as possible. We want to be able to change the functionality of these objects at runtime. And we want to be able to change the functionality of these objects at runtime. Well, from there, we'd be moving on to the composition over inheritance pattern. So that name is a bit of a mouthful, so let's break it down kind of word by word here. So starting at the word inheritance, generally in object-oriented programming, a concrete class or a leaf class gains its functionality either from methods implemented on it or methods implemented on its parent classes. So in this case, concrete class A would gain its functionality from itself and base class A. Concrete class B would gain its functionality from itself and base class B, and so on. Where in composition over inheritance, this pattern generally relates to defining the functionality of a concrete class based on its composition. So as you can see here, we define a field called behavior of behavior type on concrete class, and then just slot in a different behavior into that field based on what we want the concrete class to do. So composition over inheritance is focusing on choosing composition over the inheritance style of development in the places that it actually makes sense to do so. So what are some CM use cases for this? So the main one we're going to be talking about today is a composition over inheritance based work surface, for example. So we could have a work surface that can change its shape and its set of materials based on the behaviors that it is built up with. Instead of having to extend multiple classes out to create a rectangular or a corner surface with test materials and wood materials, you would be able to have a single work surface that can be all of these entirely based on its the behaviors that it is composed of. So let's look at the actual code of this sort of development. So as you can see here, we are defining a composition over inheritance work surface with 4 different behaviors. A shape behavior, which defines its shape, so corner, rectangular, round, etc. A domain behavior, which defines the allowed sizes. A material behavior, which defines the allowed materials. And an edge behavior, which defines the allowed edges. And for those who haven't done a lot of work surface development, edge behavior would be such a pointed edge on the work surface or a flat edge on the work surface or something like that. So when do we actually get around to using these behaviors? Well, wherever you would generally do the implementation at a base class or at the actual concrete or leaf class is where you would end up calling these behaviors. So in work surface development, the shape is built up based on a path of lines or curves that demonstrate the shape of the surface itself. So for a rectangular surface, it would be a set of 4 lines representing the front, back, left, and right of a surface. So in this method where we build the path for our composition over inheritance-based work surface, we would then call the behavior to get the path. And then if you look down a little further there, you'll see that we call the edge behavior to determine what the edge type of each of the different sides of the surface are. So what about implementation of these behaviors now? So implementation of these behaviors is fairly simple. We have our work surface shape behavior here. We have a final implementation of a get path method which we don't want changing in any extended version of this behavior. We have a edge finish type method, which has a default implementation, but it could be extended off of by different extended shape behaviors. And then we have a build path type, which is abstract, and that it must be implemented by every behavior that we develop. So that build path behavior is what you saw in the previous slide, where we were calling that on the composition over inheritance work surface. So what does this look like in implementation? Well, you would simply create a rect shape behavior, and then you would build up a path with a backside, right side, front side, and left side to create a rectangular surface. What this ends up looking like in reality is this. So as you see here, we are instantiating a composition over inheritance-based work surface with a rect shape behavior, a standard domain behavior, a wooden material behavior, and a standard edge behavior. Because we inserted a rectangular shape behavior into the composition of this surface, we get a rectangular surface. Because we have a wooden material behavior, we have multiple different domains of wooden materials. And because we have the standard edge behavior, we get the standard two edges that we developed, which are the banded edge and the knife edge. So another implementation of this could end up looking like this corner shape behavior, which has a back left, a back right, a right side, a left side, and a front side. So as you can see here, developing these different behaviors ends up being very simple as you're confining individual pieces of functionality to a single class. So you get this compartmentalization of the information that you're trying to work with. So in reality now, this one ends up looking something like this, where we have a composition over inheritance work surface that we now fill in and we compose it with a corner shape behavior. And we also, in this case, I'm changing the material behavior to use the test materials. So this could be like some sort of debug materials for your snapper. And now we kept the same edge behavior and the same domain behavior. So we're allowed to have the same sizes, and we are allowed to have the exact same edge type. So we still are allowing banded edge, and we're still allowing knife edges. But our entire shape of our surface is changed because we composed it differently. So what are some of the pros and cons of using this style of development? Well, some of the major pros you get is those behaviors, if you develop them right, can actually be swapped out at runtime. So if you were writing a surface where you needed it to snap back to back or connect left to right, you could design a snapping behavior that gets swapped out at runtime during an animation to change how the snapping works on that work surface. You also get a lot of code reusability in that you can now reuse that rectangular behavior inside of any surface that you're developing in your extension that needs a rectangular shape. And you gain a lot of extensibility in that now you can create a single work surface class that can be used for many, many, many different types of surfaces. Some of the major cons with composition over inheritance is these complex interactions between these behaviors ends up being very difficult. So if you end up in trying to develop in a situation where the shape of your surface is dependent upon the material of your surface or the domain of materials on your surface, trying to get these behaviors to communicate with each other can end up leading to a lot of weird spaghetti code and kludgy code. Also, it can end up adding a lot of overhead if you have these one-time use behaviors. So if there is only a single work surface in your extension that needs a metal material, you are going to have to go and create an entire metal material behavior for use in this one surface. So that's kind of where we're going to end with composition over inheritance. There's not much more to go on there. And last slide, we had some similar patterns, but there really isn't anything like that one. So let's just move on to the next problem that we have. So let's say we have a problem where we want to construct one or more very complex objects. And you want to be able to modify lots of different parameters on these objects. And you also want to be able to get kind of a big picture overview of the creation process. And you want to be able to, again, just like in the last pattern that we demonstrated, maximize your code reuse. So be able to reuse as much of this as possible to minimize development. Well, for this, you would probably end up using something like the builder pattern. So how this pattern ends up working is you have an object builder, which is a class whose entire purpose is to build up and then return a concrete object. You can configure this object during its creation via various configuration methods before calling finalize, which returns the object that you are building up. So what is a CM use case for a builder pattern? The one that we came up with for this presentation is the conveyor builder. So what this is going to do is this is going to create a run of straight or curved conveyors, all linked up with each other using a single builder class. So we're going to have our conveyor builder that has its add straight conveyor and its add curved conveyor method. Those are going to do each of their things respectively. And then when you've hit finalize on this builder, it is going to return to you a set of conveyors that you should just be able to insert into space, and they will be pre-set up based on how you configured them. So what does a builder look like in code? So right here we have our conveyor run builder. So we have three methods that I think are the most important to talk about here, which are the add straight conveyor, add curved conveyor, and finalize method. So as you can see, the add straight conveyor takes in a space line or a line 2D in space, and then does what it does to build a straight conveyor out of that. Generally, in this case, you'll notice that that method is returning another builder. This is another of the really, really neat things that you can get out of the builder pattern is that builders can return builders can return builders. So in this case, when you say, I want this straight conveyor, you would then be able to take the straight conveyor builder that is returned and then modify that builder using its methods to modify the individual straight conveyor that you were using before moving on to the next conveyor that you wanted to put into the run. In the case of the way that we designed this right now, you actually override the builder type on this run builder in order to change the type of straight or curved conveyor that is going to be built. We then also have, as I mentioned previously, the curved conveyor method, which does similar to the straight conveyor, but takes in an arc instead. And you have your finalize method, which is going to return this set of conveyors that you've been building up using this builder this entire time. So what does this builder actually end up looking like in use? Well, to actually use this builder, we created an animation in which a user defines a set of lines and curves all connected to each other end to end. And then when they hit finalize, the animation goes through all of those shapes that the user created and builds up straight or curved conveyors out of them, and then inserts the entire run into the drawing. So as you can see here, we are looping over, and then we're actually calling the builder add straight conveyor and calling the builder add curved conveyor. We then call finalize and insert. So right here, what would actually an implementation of this builder look like is right here, we're going to have our FredX conveyor. So as I mentioned earlier, in our implementation, we are defining the type of conveyor that is being built by the actual individual builder. So in this, we implement our Fred conveyor run builder, and we say we want you to use the Fred straight conveyor builder to build all your straight conveyors, and we want you to use your curved conveyor builder to build all your curved conveyors. And what that ends up looking like in the end is this. So as you can see, we have the user coming in and inserting sets of lines followed by sets of curves, which are defining their conveyor. Through the animation properties here. And then when they hit finalize, all of those individual conveyors get built and inserted into the drawing. And very specifically, these are the FredX brand conveyors. So another implementation of this could end up looking very similar, in which we have our Blamazon conveyors. So we do something very similar where we create a Blamazon straight conveyor and a Blamazon curved conveyor builder, which those builders would end up just creating Blamazon or straight, Blamazon straight or Blamazon curved conveyors, respectively, return them in our run builder, and use them in a very similar way that we did to the FredX one. But something that we're going to be doing differently with this builder is that we are going to be doing post-processing in the finalize method. So one of the really interesting things that you can do with another really interesting that you can do with the builder pattern is that you can actually defer the construction of all of these objects that you've been adding in right up until the point that you call finalize and actually need to return them. This allows you to get a larger picture representation of what the user is trying to create or what the developer is trying to create before you actually make them. So in this case, what we're doing is we are finding inline straight conveyors or inline curved conveyors. You'll see a little more what I mean by that in the next video, and then combining them into single straight conveyors and single curved conveyors. So if they insert 5 straight conveyors in a row, all of those at the end would end up getting merged into a single straight conveyor, and the same goes for the curved conveyors. So we can do all of that processing after the user has actually already asked for the conveyors that they wanted, because we have this ability to defer the construction until the finalize method. So now what does that actually end up looking like in the end? Well, it ends up looking like this. We have the exact same animation, but just a different builder. The user comes in and inserts a bunch of straight conveyors again, followed by a set of curved conveyors. And you'll notice I'm doing these curved conveyors in line 2 at a time so that there's 2 going in the right direction, 2 going in the left direction. That's just to demonstrate the post-processing merging of these conveyors. So then when you actually hit finalize, you end up being able to see that each of those straight conveyors we built actually got merged into a single conveyor at the end. And the same goes with the curved conveyors that we built got merged into a set of curved conveyors at the end. So that is kind of, so that just really shows one of the really cool things about the builder pattern. So what are some pros and cons now, again, of using this specific pattern? Well, as you saw, it adapts really, really well to user interface. So generally, when you have a user designing something in a piece of software, they're saying, I want this, and then this, and then this. Go. And that's basically just how the builder pattern works. So you can sometimes do a one-to-one mapping of functions to user interface. It's very extensible. As you saw, we created one insert animation for these conveyors, just slotted in different builders and got wildly different functionality out of the other end. It isolates the construction code. So instead of having to have all of the construction code to build these long chains of conveyors inside of the individual conveyor classes, we've isolated that to the builder. And as I mentioned earlier, it allows for deferred construction. So there are cases where you might not even need to create things that the user asked for because the user asked for something that directly contradicted for something that they previously asked for. This allows you to just not do that because you're not actually doing the construction until the very, very end. There's really one major con to using this pattern, which is it adds a significant increase to code complexity for something as simple as building up an object or a series of objects. You get a lot of functionality, but at the cost of a lot of development. So just for the FredX builder alone, we ended up having to have 2 separate builders, one for each individual type of conveyor, and then another builder for the run of conveyors. And the same thing goes for the Blamazon conveyors that we used. So kind of ending out this presentation here, we've talked about only three out of, oh, sorry. We've talked about only three patterns, but there are a lot that are also similar to the builder pattern here, where we have the factory method pattern, which is fairly simple in that you're creating a single method with a set of parameters that returns an object that it builds. A constructor is actually an example of a factory method pattern. We could also talk about the prototype pattern here, which is entirely based around cloning individual objects in order to construct lots and lots of them. So let's say that there's a very high instantiation cost for an object. Well, you can just instantiate one of them, clone it a bunch of times for every time you need one. That's the prototype pattern. An abstract factory pattern is very similar to builder pattern, but with some modifications that make it better for certain use cases. So where do we go from here? Well, as you've seen, there are some pretty cool ways that we can apply specific patterns to development in CL. And there are a lot of these. And they are all designed to solve very specific problems. I mean, just going through some of these here, the flyweight pattern is used to minimize the number of objects. It's very similar to a caching style pattern. The singleton pattern is for when you need a single object a single instance of an object to be used inside of your software, and you don't want many of them to be instantiated and then passed around. The iterator pattern for looping over sets of objects where how to find what the next object in the sequence is might not be so trivial. I mean, there's many of these patterns, and they provide some well-tested implementations of solutions to very common problems. So if there's one takeaway that I think is the most important out of this presentation, it would be always double check that the problem that you're trying to solve hasn't already been solved. And one resource for solving those problems might be these patterns. Thanks for being in this presentation. Do I have any questions?